and this variable here, y, the ones that were in our picture. Does anybody at this table have any equation you can think of that somehow connects x and y together? X, y, and you can use this picture however you want. The Pythagorean identity. Okay. Now I'm curious to know how many of you knew that. I mean, now that you say it, how many of you still don't know what the Pythagorean identity is? If I have a triangle and somebody gives me this side is A, this side is B, and this side is C, and this is a right triangle, the relationship is A squared plus B squared equals C squared. I'm hoping that everyone in here knows this. If you don't, this is really going to be impossible until you know it, right? This is a standard formula from, I guess, basic geometry at some point. Now, I understand you probably haven't used it in a long time, but now that you see it, does that look familiar to you? Okay. So I asked you to give me some equation that connects x and y together, and you said Pythagorean. Can you elaborate on that? Can you tell me exactly what that equation would be according to our picture? X squared plus y squared must be 24. 24 squared. I forgot to say squared. Do you all agree that that equation goes with this picture? Yes? This is it. This is the big daddy right here. This is what we need. Because now that I have an equation, I can differentiate it. I can take a derivative if I want. I can differentiate it. But what should I differentiate with respect to? This is going to be kind of way out there now. What should I differentiate with respect to? X, y, or something else? Look at what you're given and what you want. This is the rate of change in x with respect to time. This is the rate of change in y with respect to time. So I should take this equation and differentiate it with respect to time. Let's just do it and see what happens, right? Again, this is our first example. I think I'm going to put it right here. So taking this equation right here, I'm going to take the derivative with respect to time on the left side, and I'm going to take the derivative with respect to time on the right side. So do you see implicit differentiation kind of now? What is the derivative of 24 squared? Well, 24 squared is a constant, right? So derivative constant is 0. So the right side's easy, I hope. Here's the challenging part. We are differentiating with respect to what? Time. Time, not x, not y. You'll see why we're doing time. After I finish this next line, you'll see why I'm doing it. What is the derivative? Oh God, I'm scared. What's the derivative of x squared with respect to time? You need to use the chain rule. So 2x first, right? 2 comes out, then x to the first power, then times, what is the derivative of x with respect to time? dx dt. It's not 1, it's dx dt. Do y'all see what I'm doing there? 2 comes down, power comes down by 1, but then I take the derivative of x, but with respect to time. Had this been with respect to x, the answer would be 1. But it's with respect to time, so I have to put dx dt. Then I say plus, let me move this over a little bit. What is the derivative of y squared with respect to time? 2y times dy dt. Have you ever heard that phrase, like the wheels are coming off? Have you ever heard that phrase? No, the wheels are coming off. I think it means like you're driving down like a race car and the wheels start falling off, and I just feel like the wheels are coming off here. Y'all all right? All right. So if you follow me up to this point, why am I happy about seeing that equation? Why am I happy to see that? Because you can start plugging everything in. Look, what is it that we wanted to find? dy dt. It's there. It just appeared, didn't it? It just appeared in our equation. The thing we're looking for is sitting in an equation. What about everything else? Do we know dx dt here? Do we know what this is? Yes. That's 3, isn't it? Do we know what y is at the particular instant in time we're talking about? 5, yes, y is 5. I'll put check mark. Do we know what x is at the particular instant in time? So you have to go to this picture here. Remember, this is y, right? This side is x. Can you tell me what x is? If I give you this side and this side, can you find this side? Yes. In fact, you can go back to that a squared plus b squared equals c squared. So I'm going to be able to get what x is, and then I'll have everything, and I can just solve for dy dt. So let me finish this problem up. I know it's giving you all a headache now. Okay, so do you all agree? I have this. This is what I want to find. This one I don't have directly. I need to just go find it real quick. Okay, so let's find the x. Using this exact moment picture, I know this is 5 and this is 24. This is x. I know x squared plus 5 squared is 24 squared. And I need someone on their calculator to go ahead and do 24 squared, then subtract 5 squared. What is it? Oh, you already took the square root? Yeah. Yes, so x is 23 point what? 47. Okay, so x is 23.47. So now I'm just going to go to this equation. I'm going to plug everything in. Here we go. 2 times 23.47 times dx dt. What was dx dt? 3 plus 2 times y. What was y? 5 times dy dt, which I don't know. That's what I'm looking for. That must equal 0. So now all you're going to do is isolate this. So on your calculator, do 2 times this times this. Take that answer, move it to the other side, and then divide by 10, because 2 times 5 is 10. I'm just going to double check it here. All right, so when you do this, you should get 140.82 plus 10 times dy dt equals 0. So that's what you get when you multiply those. Then I'll move this to the other side. I get 10 dy dt equals negative 140.82. And then I divide both sides by 10. So I get my final answer, dy dt is negative, is that right? 14.082. Okay, yeah, we need to talk about what the units are in that. Why is our answer negative?
It's going down.
Because y is shrinking, isn't it? Y is getting smaller. Because it's shrinking, we get a negative answer. So as you pull this ladder out from the bottom at 3 feet per second, at the exact moment that this is 5 feet off the ground, that point is moving at about 14 feet per second. That's a lot faster than you're pulling it out, right? So 14 feet per second. We obviously need to do some more problems, right? Like, you can't just do one and be comfortable. We're going to do problems like, you know, you have like, let's say you have two planes and they're flying away from one another like this. You can start talking about how fast is the distance between them changing. And I don't know how deep they go into this.
Cylinder, or not a cylinder, but like a cone in the water.
Yes,
Like that.
yes, you have a cone like being filled up with water. How fast is the water level rising? Yes.
Those, I hate those.
Yeah, those, we probably won't do that in
More
here.
like regular kind of.
Yeah, that's regular calculus. Okay, I guess we're done, right? Everyone's turned in that thing from earlier, and have a good weekend. See you on Tuesday.
There's also like a,
Do your homework for 11:05.
there's also the problems with like a shadow. And
Yes.
Yeah.
Yep, yep. You got like a light pole, and then you got someone running, and you've got their shadow moving and stuff like that. Yeah, yep. If you have it like that, I'll just turn in the whole thing.
In this class, are we going to be doing what's it called?
Let me turn this off.
Oh,